Fantastic. Okay, we continue our journey through proving Gödel's first incompleteness theorem. So what we are heading towards is, as I have kept saying, the most important part of the entire theorem, which is pretty easy to state. It's just that the general recursive functions are representable. And I'm not going to quite get to this today, but I'm going to perform the major proof reduction that is performed in proving this result. So this is the beta lemma, or Gödel's beta function you might have heard of before. It's semi-famous, I suppose. If you haven't heard of that before, no worries. I'll be completely introducing all of it today. But the essential point is that we want to prove that all of the general recursive functions are representable, which means that if I have a general recursive function in my hands, there is some formula inside Robinson arithmetic which represents this function, meaning that it reflects the mapping of the function in hand. Now, the way that you would prove that is by going through the definition of the general recursive functions and constructing such a formula for each clause. So you go through the base cases and then you go through the inductive stages. Now, let me just pause on the inductive stages at the moment. We know that the way that you build a general recursive function is you're allowed to compose general recursive functions and you end up with a general recursive function, but you're also allowed to perform primitive recursion, and you're also allowed to perform primitive minimization, as I called it in the last lecture. Now, composition and primitive minimization is not so difficult to achieve representability for, but primitive recursion is. Essentially, the problem is that the obvious choice for a function, sorry, for a formula representing the primitive recursion of two general recursive functions is kind of given by an infinite disjunction, and we don't have that available to us inside this language. So the standard reduction is to prove that, in fact, we don't need to have the clause of primitive recursion inside the definition of a general recursive function. So let me write something down. The aim for today is to come up with a simpler definition of the general recursive functions that still capture all of them. And then those are the functions which I'm going to prove are representable. So come up with quote unquote simpler definition or characterization of the general recursive functions. Then prove that these are representable. Okay, so let's get some precise stuff written down on the board. So just to remind you, a function f from some power of the natural numbers to the natural numbers is representable if there exists a formula f, and this has three variables inside it, x1 up to xn as well as y. Y represents the output of the function. And here is our first order language that we're working with, consistent with the previous lectures. And we ask this to satisfy the following. If f of n1 dot 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 nm is equal to k, then inside Q, I can prove the following formula. For all y, f of n1 underline dot 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 nm underline y, go on to the next line, if and only if y is equal to k underline. So just remember the notation that the underline of a natural number is the representation of that natural number inside Robinson arithmetic. So for example, 2 underline is, Billy hates it when I say this thing in names, but he's not here today. So 2 means the successor of the successor of 0. Okay, great. And then the definition of a formula being representable is similar, but it's not exactly the same, as a matter of fact. I won't give the definition of a representable relation right now because I won't be using it today. I will be using it next time. But what is worth keeping in mind at the moment is that the fact that the general recursive relations are representable is going to follow as a corollary from this theorem that the general recursive functions are representable. Okay. So, as I said, in order to do this, we want to come up with a reduction, not a reduction, I don't know what to say, an alternate classification of the general recursive functions, which is going to be more amenable to the proof that we want to write. So let me move to the next board in order. Characterization, that's a good word. Okay, let me move to the next board. Okay, have people followed me? Dan, do you need to be near me to keep recording? Do I need to wait for you? I'm confused. Oh, okay. Sorry, you've probably explained that to me about 20 times, but I forgot. Okay, cool. Okay, so let's write a definition. So this is my simpler characterization of the general recursive functions. So I'm going to call the set of such things phi. Okay, so I'm going to make the inductive clauses simpler, but there's going to be a price for that. The price is that I have to make the base cases more complicated, and it doesn't make them more complicated, it's just going to be more of them. But once you see the base cases, you'll agree with me that it's definitely a worthwhile trade-off. Okay, so we still need the constantly zero function. The successor function. We have the projections. Whoa, sorry, it's getting a bit messy on the board. Okay, so this is what we had in the original definition, but the extra stuff is going to be the addition function, the multiplication function, and then also need the characteristic function of the relation given by the diagonal. So that's just the characteristic function of the equality relation. Oh no. Yeah, and recall that my characteristic functions are a little bit non-standard in that when the relation, when the argument is in the relation, I map to 0, and when it's not, I map to 1. There's not a 6, that's a 0. Okay, now let's get to the interesting part. So I'm going to have minimization still and composition, and that's it. That in fact is sufficient. So first I'll write composition. Let me clean up this board a little bit. Okay, and lastly, what I've been calling primitive minimization. So it's just minimization, but I need to only do that on general recursive functions which do admit an argument that maps to 0. So let me make that precise. Okay, so I'm ranging over all n-1 tuples of the natural numbers. So that does say n2 ... up to nm. So for all such things, there exists n1 in the natural numbers such that f of the induced tuple is equal to 0. Okay, so if I have such a function in my hands, then the following function is general recursive. So I denote it by mu f, and this goes from n-1 tuples of natural numbers to the natural numbers. And what it does is it gives me, it takes n, n2 up to nm and returns the minimal such n1 such that f of n1 up to nm is equal to 0. I'll simultaneously introduce some notation as well. So it's sometimes helpful to refer to that minimal integer as mu n dot fn n2 up to nm, which equals the minimal. If not, let's move to the next board. Okay, so the key lemma is that this gives us all of the general recursive functions. And I wish to prove this to you. Okay, the sketch of the way that I'm going to do this, it's a very clever idea. So first and foremost, it's not very difficult to prove that the extra functions that I have in the base case are general recursive functions. And I'm not going to prove that. That's completely elementary. And I've already shown that some of them are general recursive. in fact. The difficult part is making the observation that inside the inductive structure of the definition of the set phi, we did not use primitive recursion. So I need to say that given a general recursive function, which is defined by primitive recursion via G and H, say, that there exists a, that this function is an element of phi. That's the difficult part. Now, the general approach is going to be to make use of a what's called a beta function. So a beta function has a particular property, and it's not going to be clear that such a thing exists. So first I'll state the property, and then there'll be some work involved in proving that such a beta function exists. Then once I have the beta function in my hands, I can then use it in order to prove the result. But let me give you a general rundown of how this is going to go. So the sketch is, say I had a function which was defined by primitive recursion. So this is a function from n plus 1 tuples to n, and I'm saying that there exists general recursive G and H such that the following holds. So f of 0, n1 up to nm is equal to g of n1 dot 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 nm, and f of, say, k n1 dot 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 nm for k greater than 0 is equal to h of k minus 1 f of k minus 1 n1 dot 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 nm, and then I'm also allowed to use the data of n1 up to nm itself. So we think about these as recursive functions, if you're familiar with such things from computer science. Okay, if we have such a thing, then what we can do is we can identify some value fk n1 dot 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 nm with the k plus 1th element in the following sequence. And all you do is evaluate all of the values of f 0, n1 dot 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 nm, and then f1 n1 up to nm. So I can calculate this value, and I can calculate this value. Okay, and that's a finite sequence. So that doesn't seem so genius yet, but the reason why this is so clever is because what we're going to do is come up with a way of encoding finite sequences of natural numbers by single natural numbers. Okay, so a whole finite sequence of natural numbers will be represented by a single natural number, and then we're going to have a function beta which can decrypt this encoding. Now, it's beta which we require to be a general recursive function. It's not actually the encoding that beta unwinds that needs to be. So the goal is to construct beta from the natural numbers product of the natural numbers to the natural numbers, such that for every sequence so I haven't written this very clearly. I'm ranging over all possible lengths of all finite sequences as well. Okay, so let's have a look at this. What's happening here is I'm saying that for every finite sequence, y naught up to ym, there exists some natural number d. So we think of that as the encoding of this finite sequence via a single natural number d. Now, I'm not asking for that to be computable or anything. I'm just saying there exists some natural number d, which is an encoding of this sequence. And then we require that or the property that we need beta to satisfy is that it can decode this integer. So beta of d comma I will read into d and work out what the ith element of the sequence that d is has encoded is. And then we'll also need that beta is inside phi.
Hey, Will.
Yeah. Oh, hey, Billy. How's it going?
Hey, good. Just a question. So it's saying there exists a d, and then this last equation needs to hold for all I up to like m or something, or k or whatever it is.
Yeah.
For all the same d.
Yes, for the same d.
Yeah. Okay. And just about the lemma. This is I don't know if you explicitly said it, but this looks like it's for like it's about like a function defined by primitive recursion, or I guess that could be, or something.
Oh, sure. So,
well, when I say by primitive recursion, I mean like specifically that induction step in defining all the general recursive functions.
is that the problem that you have? So the point
No,
is that
I wasn't pointing out a problem. I was just sort of
oh,
trying to understand how this lemma is going to be applied. Is that this f, g, and h is like the same f g, and h from like defining a function via primitive recursion.
yeah, that's exactly correct, right? So we have this extra construction inside the general recursive functions, which I've referred to as primitive recursion, which is exactly what I've written here. It says that if I have g and h, then I can combine them in this way to construct f, and then f will, by definition, be a general recursive function. This is missing inside the definition of the set phi. So I need to show that I can reproduce it using the machinery that I have there. And the way that we're going to do that, and the way that we're going to do that is identify the kth value in the first entry of a function defined via primitive recursion with its finite sequence, the final element of the finite sequence up to that point. So if I have some decoder for all of the sequences, then I have a decoder for that sequence. And so now all I need to do is show that beta is an element of phi, and we've actually mimicked primitive recursion. Does that make sense?
Yeah, cool.
Yeah, and there'll be work involved in that, but we'll get there. Great, I'll move to the first board again. Congratulations, Billy, as well. It's very exciting.
Congrats, Billy.
Thanks.
All right. Now back to the math. So let me get a formal definition of a beta function down. And I refuse to write in blue. So let me write that in black. Okay, so I'm going to have a family of functions that identify, so all of what I was referring to as the encoder, so I take finite sequences and encode it via a simple natural number. I'm going to formalize that with just a collection of functions, right? So the way you think about alpha k is that is the encoder for the length k sequences of natural numbers. So all of these functions are required to be injective. For every finite sequence of natural numbers, we have, and so this is an important one, beta of alpha m plus 1 of y0 up to ym, comma I is equal to yi, right? So you encode y0 up to ym using alpha m plus 1, and then use beta in order to decode the ith element. And oh, this contradicts what I just said. So no, it doesn't. So you asked if it was the same D for all. You asked if there was the same D for all M, and I am asking for that because they're all equal to the same thing: alpha m plus 1, y naught up to ym. Okay, and then lastly, we just need this function beta to be inside our set phi from the very start of the lecture.
What's up with the m plus 1? So we're sort of...
Oh, just bad notation I've used.
We're not using alpha 0.
Yeah, we're not using alpha 0. I wanted to have my subscript starting at 0 for some reason, which meant I had to, I could have...
We're not playing Go here.
I don't get it. What's Go got to do with it?
We're not using alpha 0.
Oh, right. That's very clever. So I have to have an awkward +1 somewhere, and that's where I decided to put it. Okay. Now this is really, really cool. What happens next? I think this is a really slick piece of mathematics. So the way that we're going to do this is we're going to use the Chinese remainder theorem, right? And if you think about it, that actually makes perfect sense because the Chinese remainder theorem tells you that if I map a single natural number into a sequence of them, then that thing ends up in isomorphism under particular circumstances. So that's just telling me how to represent a sequence of integers via a single integer. So that's a very good place to start. That's a rundown for those familiar with the theorem. Let's recall it. So the Chinese remainder theorem tells you that if I have a sequence of pairwise coprime natural, sorry, not pairwise, they all, wait, what is it? No, I need no common factor amongst any of them. So x0 up to xm are coprime natural numbers. And I can denote by x their product. then the following is an isomorphism. C for Chinese. Let's state it correctly. Okay, where the angle bracket, sorry, just the brackets stand for the equivalence class. So this is M mod X, for instance. Okay, that's an isomorphism. So all that we really need to do is what's going to end up happening is this sequence is going to be y naught up to ym, right? Modulo x naught up to xm, so there will be a bit of cleverness involved in our choice of x naught up to xm. We need for all I that xi is greater than yi, right? Because if we don't have that, then taking the equivalence class, taking yi modulo xi is going to chop yi up, and we don't want to do that. So we can pick x naught up to xm to satisfy that, so that doesn't happen. And then we're going to pull back and look at this equivalence class that maps onto that sequence, and then we'll just take the least positive representative of that equivalence class, and that is going to be our choice for alpha m plus 1 of y naught down to ym. Okay, so I haven't explained how we're going to define a function beta that unwinds that yet, but it's obvious how you unwind it. You just take the equivalence classes, which is simply a matter of dividing enough times until you observe your remainder. Now that function, the function that observes the remainder upon division, that's general recursive, right? So this is really what's going on here. Like, the point is the Chinese remainder theorem has two maps, a forward one and a backward one. The forward map is completely computable and constructive and easy. Going backwards is also computable and constructive, but it's actually not important to the theorem. We're just going to black box this and extract from the sequence the representing integer, and then we're going to prove that to unwind that is general recursive. But that fits with our intuition that it's a computable function. Okay, does anybody have any questions about the sketch?
Maybe you could briefly explain what Z mod X is.
Sure.
Benefit some people.
Okay, so when I write Z mod, let's take an explicit example. So 5Z, for example, is, do I want to give the actual definition? So it's the equivalence classes modulo the ideal 5Z inside the integer ring Z. I don't think that's helped anybody. So let's write represents modular arithmetic. So I don't know. A little bit. Oh, it's so cool. I think it's so snazzy. You don't really do anything more clever than this. So this theorem holds a lot of weight in this theorem itself. It's very cool. Okay. And then
I guess the addition structure on that group is like not super relevant to, at least not the data of like C.
Oh yeah, sorry, I wanted to say that. Yeah, I'm only going to use the bijective quality of this isomorphism. I'm not going to use the additive structure in any of this. Obviously use it in the proof, but I'm not going to use that in the encoding or in beta, anything like that. Okay, I kind of hate myself for what I just wrote, but I'm going to move on with my life and not think about it. Let's get to the next board. Okay, so as I said, we need to take a clever choice of the xi, and that's what I want to explain. Sorry, I just noticed the time. Dan, how pressed for time am I? Do you need to move on? Is there something at 9?
He's over there. Oh, he should have heard you though. He's got the halo on.
I don't know whether, because I'm about to go into the Chinese remainder theorem, etc.
Let me just check the schedule. On the website, there's a tea break from 9 till 9:30, and that seems to check out.
Okay, can I just keep going in that case, do you think? Okay, thanks. Okay, so this is a clever point, right? Like this is where you'd have to, this is where you have to be a bit smart, right? Okay, so the choice that we're going to take is the maximum of m, the length of our sequence, along with all of our elements. And then we add 1 to that. And then for I equal to 0 up to m, define xi to be 1 plus I plus 1 multiplied by j factorial. This is a very clever choice. This is going to satisfy the following properties. And we know what the properties have to be, right? You know exactly what I'm about to say. I just need this to fit into the Chinese remainder theorem in a way that will allow me to encode an integer, not an equivalence class. So what I need is x0 up to xm to be relatively prime. And I need yi to be less than xi. Okay, so let me prove this. It's not too difficult. So first, let me show that all of the xi are y prime. Oh, no, let me not use j. Let me use k. Okay, let I be different from k and consider the difference of xi and xk. That's 1 plus I times j factorial multiplied by 1 plus k times j factorial, which is equal to I minus k j factorial. Okay? Now, if it was the case that the xi and the xm were not relatively coprime, so say there was a common divisor of xi and xk, right? So say p say p divides this, then the point is p must divide either I minus k or j factorial, right? But I minus k is at most n, and we've chosen j to be greater than n. So therefore, if p divides I minus k, that means that p can't divide I minus k, and so therefore p divides j factorial. So let me write that on the board. I want to move up here. Say p divides I minus k times j factorial. We notice that I minus k is at most n. And we chose j to be greater than n. And so what that means is if p divides I minus j, then p must also divide j factorial, right? Because j is greater than n, and so therefore if p divides I minus k, that is, p divides a number that is less than j, and j factorial is the multiplication of all numbers less than or equal to j, and so therefore p would also divide j factorial. So the point is p dividing I minus k implies p divides j factorial, right? So we can assume without loss of generality that p divides j factorial. Okay? But if p divides j factorial, then p can't possibly divide xi, because xi is 1 plus I plus 1 j factorial. And so the division by p would give you a remainder of 1, and that's a contradiction. So what am I doing? Sorry, let me... A contradiction. Okay, and the second clause is very easy. We just need to show that yi is less than xi, but we have yi is less than j, which is obviously less than j factorial, which is less than xi. So that one's very easy to satisfy. Okay, and that's a proof.
Cool.
Let me move on to the next board. Okay, so now we need to move on to showing the existence of a beta function that decodes this encoding. Or actually, I guess I should say, I guess I should define the alphas first. So let me give a definition. So alpha, was I using K earlier or was I using M? Let me just use M. Alpha m plus 1 of y naught up to ym is equal to the inverse map of the Chinese remainder theorem that I gave you, applied to the equivalence y naught, the equivalence class of y naught modulo x naught, and then up to ym xm. So that's not entirely true. Sorry, it's not equal to that. That gives us an equivalence class. So let me get rid of this equality. So that gives an equivalence class. Okay, and then let alpha m plus 1 y naught up to ym to be the least representative of this equivalence class. Okay, now we actually need to identify a subtlety here. So what we now want to do is construct the function beta, right? Now, the problem is it seems like we're able to construct. It seems like we're able to encode this sequence using this integer that I've written, right? But the problem is if I was just given this integer, so if I was just given alpha m plus 1, y naught down to ym, right? So that's some integer, call that d. If I was just given d, then I would need to feed that through the function c in order to decode it. But c would have to know what x naught up to xm is, right? And x naught up to xm were all defined in terms of j, and j was defined as the maximum of m y naught up to ym plus 1. And so therefore that Chinese remainder, the map given to us by the Chinese remainder theorem, actually needs to know the sequence y naught up to ym in order to even exist. So that's actually circular. So let me highlight this subtlety. So let alpha y naught, alpha m plus 1 y naught up to ym equal d. Now, c of d is our sequence, but to define c, we need x naught down to xm, where xi equals 1 plus I j factorial, where j factorial equals the max of m y naught up to ym plus 1, i.e. we need to know y naught down to ym to decode c of d.
So when you say C, there's really a bunch of implicit subscripts.
Yeah. The subscripts are the x naught down to the xm, or they're the y naught down to the ym. You can also get it from that information.
Mm-hmm.
Well, actually, it's the x naught down to the xm. That's the map coming from the Chinese remainder theorem. But you have to a priori have chosen those co-prime integers, right? And we built them based off the sequence that we began with. So this is actually circular. This idea won't work on the nose. So the solution, and again, this is just such a piece of sleight of hand. I still haven't quite worked out in my life whether I'd admire or hate these kinds of moments in maths. But the solution is, well, I could also just give beta the integer j factorial, right? If beta had access to the number j factorial, then it would just be able to construct this x naught up to xm without any knowledge of y naught down to ym, and then successfully decode the integer.
Mm-hmm.
Okay, so that works, but the problem arises. Now the beta function is going to ask for two integers in order to decode c of d, right? The two integers are c of d itself and j factorial. So I need to come up.
I thought the beta function was already had two inputs. Do you mean like three inputs?
Yeah. Sorry, what I meant was it would need two inputs corresponding to the integer. God damn it. It would need two inputs corresponding to the integer representing the finite sequence, and then we'll need a third one representing whichever element inside that sequence that you want, right?
So the normal, like, original goal for the beta function, the two arguments were an encoded thing and an index that you want to extract from the encoding.
Yes. Yes.
But we're adding to that an extra argument, which is j or j factorial. Or...
j factorial, or either. But what am I going to use? I'm going to use j. Yeah, so I'll give it j as well.
Yeah.
Okay.
Oh, as in it's sort of being encoded alongside the, like, it's D and J are going together in the same argument.
Yeah. So I need to combine D, C of D and, no, not C of D, D. Yeah, I need to combine D and J into a single integer. And then beta needs to be able to separate those two integers, work out what the pair of them are, and it needs to be able to do that using general recursive functions. So it's not super simple to pull off. Now, let me just, I won't say the first two. Let me say D and J, and then I. Okay, I'll explain how I do that back over on the first board.
Okay, you're at about 9:14, by the way.
Okay, so now what we're going to do is introduce some new functions. So I'm going to have capital J. It's not very important what this is. I just need it to be injective from n cross n to n. Oh no, sorry. I need it to be injective, and I also need it to be general recursive. Like I need it to be an element of the set phi that I've introduced at the start of the lecture, right? So it has to be quite a simple injective function from n cross n to n. I didn't come up with this one, but I found it. So this is what we're going to work with. And then I also need to be able to extract from this what x and y are. So I need projection functions. You can think of it as. And these are defined as follows. So we take the minimal x prime less than or equal to y, such that there exists a y prime less than or equal to x, where x is equal to j of x prime comma y prime. Okay, so the point is j is injective, right? And so when I look for the minimal x prime for which there exists a y prime less than or equal to x for which x is equal to j x prime y prime, I can give as input x here the value jxy. And then by injectivity, that's going to go into that injective function and pluck out xy, but it's going to throw away y. And so this function k just returns the value x that you gave to j. A similar one exists for the y value. We'll call this L. And this is just the minimal y prime. Okay, so we define these, and then the lemma is that J is injective. And then we also have for all x, y, an element of n cross n, the following. So k of j x y comma j x y is equal to x, and L of j x y j x y is equal to y. Okay, I'm not going to prove this, and I'm not going to go through the calculations, but let me give you an idea for it. So as I already said, we think about J as encoding. It encodes a pair of integers a pair of natural numbers as just a natural number, but then we want to be able to extract those two natural numbers from that pairing, and that's the role that K and L play. Now, it looks a little bit weird because we've got these minimizations here. The only reason why they're there is because we can only perform minimization to functions that we don't know evaluate to 0 for some input if that minimization is bounded. We need that in order to remain general recursive. So the minimization thing is just there in order to ensure that we have a minimization function, but then you might get worried. You might be worried that there is not the value x that is needed less than or equal to y prime, for which we can extract the original value x. But that's fine, because what we can do is we can just give, for this input, j of xy itself. Then there's no possible problem. The point is j is increasing, right? So the core observation is that the x, if I have a pair of natural numbers, x, y, and I map that pair along j, then I end up with a value which is strictly larger than x and y, right? And so I don't have to look for the minimal x value across all natural numbers. I only need to look for the minimal x value that is less than j of xy. Because if it doesn't exist there, it's not going to exist anywhere. And then that has the added benefit of ensuring that I remain general recursive because I've only used bounded minimization, not arbitrary minimization. Okay, that's the core idea. Does anybody have any questions?
I'm a little confused about like if you can apply, like it sounds like you're saying something like you can apply minimization to like any situation where you are doing bounded minimization or something, but I
Yes.
don't know if it really makes sense. Like, what if within that bound there is no such minimizing value?
Oh, then you just take the value y. So yeah, I didn't mention that. So the claim is that if I have a relation R, which is general recursive, then the relation which is, the function, which is bounded minimization, so the smallest x prime less than or equal to y, that satisfies that relation. Or if there is none such, just returns the value y, that is a general recursive function.
All right. Okay.
Does that make sense?
Yeah.
Okay, yeah, that was a good point. I should have said that. Cool. So now we're nearly done, where I can actually wrap up on the next board. So let me move over there, and then I will do so. Okay, so I can now define my beta function of this j, k, and l. So definition, what I'm going to do is start off with beta star, which is the map with 3 inputs. and it sends L, Y, I to the remainder of 1 plus I plus 1 L factorial when divided by Y. And the point is this is general recursive, or an element of phi, rather, from the start of the lecture. And then beta is going to be the map which sends yi to beta star of ky ly I. Okay, so we think about y as the natural number that encodes the pair of natural numbers ly in the previous function beta, and then those two inputs are one, the natural number corresponding to the sequence in question, and the other one is j factorial. Okay, and then the lemma well, I want to save time, so I'm just going to say this is a beta function. And I think it's clear from what I've said as to why. And so now what I can prove is the main proposition which I wanted to prove, which is that this is sufficient in order to simulate primitive recursion. Yeah, I don't really have time to state the proposition. What I want to get to is this eraser. Okay, let me write the crucial line. So define the following relation. So dy n1 up to nm is an element of R if and only if the following holds. Beta of d naught is equal to... Oh, I've got my notation mixed up, damn. So what did I use at the start? It must have been... I don't remember, damn it. Okay, sorry, my notation might be inconsistent here. Okay, so the way that you read this is the 0th element of the sequence D is the 0th, it is our primitive recursively defined function with 0 as the first input. So that's just meant to be one of the two functions that is used in our definition of primitive recursion. I think that I used F, but I don't really remember. Okay, and I haven't figured... Was it G? Okay.
Yeah.
Oh no, my iPad's disconnected. Oh, I might have to come back to this later. It's probably not worth rushing it anyway. Sorry, I think I don't know what's happened. My iPad's got this error code. It's yeah. Isn't it just? Oh, and I've just been kicked from deprecation. So I'm here on my computer, but my iPad's gone. Okay, I'm gonna have to leave it on the biggest cliffhanger of all time. What I'm going to do in a sentence is I'm going to define the relation that tells you that the ith element of a sequence represented by a natural number d is the primitive recursive function evaluated with I as the first input, right? And then for any integer n, if I want to know what the value is of my primitive recursive function with evaluated with n as the first input, I just read that sequence represented by d and look at the final element of it, right? Okay, and so I look for the minimal d, so the minimal natural number that encodes that sequence. And then I use that Chinese remainder theorem map in order to work out the ith element of that sequence. And that is going to be the ith value of that function defined via primitive recursion. Okay, so that's the trick that I want to use, but I'm going to have to write that out on the board next time, unfortunately. Thanks for listening.
Slick.
Yeah, very slick. Lots of tricks.
Thanks, Will.
No worries.